The first speaker that we will have here in the first session, which is called Evaluate Inputs Used to Estimate Stock Reproductive Potential, will be Ivan Lambert from Canada. He's in the Montjoly lab, and he has been with FRESH and also the NAFO working group from the very beginning, and I'm very happy that he agreed to give this keynote of this session. The talk that he's been giving, that he will be giving, is called Changes in Reproductive Traits of Fish Stocks, the Impact on Reproductive Potential and Consequences for the Reproductive Rate and Productivity of Stocks.
Okay. In my presentation, I will look at the variability in the different life history characteristics that are influencing the reproductive potential and see how those changes could influence the reproductive rate and productivity. Reproductive potential is defined in different ways, but in the literature, in the majority of studies, it's usually defined as the annual total egg production. And based on that, it's the major parameters that will affect total egg production are the number of fish at age, the proportion of females, and the proportion of females that are mature at age, and also the potential number of eggs that are produced by a female at each age. Growth will also be very important because growth rate will influence the size at age, and everybody knows that size is really important in determining the fecundity. There is evidence that spawning stock biomass do not always represent a good proxy of the reproductive potential. It's not really surprising since total egg production is dependent on several life history traits that have been shown to be very variable. This variability in reproductive traits is species-specific. Depending on the physiological limits of each species, you'll have a set of possible variation. It will also be influenced by the environment. Depending on the range in physical or biological conditions, you'll have more or less variability in these traits. And it's influenced by human activities. For example, everybody knows that size selectivity can be caused by fishing, so this will affect also the life history traits. And the other thing is that all those life history traits are not independent of each other, so some changes in one parameter will also affect other parameters. The objectives of the presentation is to explore this variability in total egg production that is associated with change in different life history traits, and to examine the relative importance of these traits on total egg production over time, and also to explore the consequences of these variations on the reproductive rate and productivity of stocks. To do that, I use the Atlantic cod population from the Northern Gulf of St. Lawrence, on which I am working for a couple of years. I use that stock because we know for that stock that there were a large variation in the stock abundance and fishing effort over time, and that also that there were important changes in environmental conditions that were observed during the same period, and that we were able to build time series of different life history characteristics for a period of 26 years, and that significant changes in these parameters were observed over time. So to give you a general idea of what happened in that stock over that period of time, I'm presenting some information on the abundance, fishing effort, and mean temperature in the Northern Gulf of St. Lawrence. Data are presented in the standardized form, so each value is subtracted from the mean values for the whole time series for each parameter, divided by the standard deviation. So what we see is that the stock abundance reached a peak in the mid-80s, and after that it decreased very rapidly and collapsed in the period of 1992 to 1994. After that period, it stayed at low level since then, so there is no recovery that has been seen in that stock. If we look at the fishing mortality, it was more or less stable for the whole period between 74 and 89 at around a mean value of 0.48, and it increased sharply after that probably because the catches were maintained at high level during the period where the spawning stock numbers were decreasing very rapidly. So this resulted in very high mortality rate. After that, there was the fishing mortality was lower and variable due to some periods of moratorium and less fishing effort. And now the last parameter is the annual temperature, mean annual temperature at 150 meters and 200 meters. Those temperatures were high in the early period, and there was a major decrease in the end of 80s, beginning of 90s. There was a major cooling period in the Gulf of St. Lawrence during that period that was observed for a period of almost 10 years in a row. And in the 2000, we saw an improvement in the temperature conditions. Here I present a kind of summary of the changes that were observed in the different life history parameters that are responsible for the egg production of the stock. So here it's the first one is a kind of proxy for the age diversity. So it's the proportion of 6+ fish over the adult population. So we see that over time there was quite important changes, the variation being observed, like at the lowest time, those fish represented 15% of the adult population, while in other periods it represented 30% of the fish. So there was quite large change in that. The sex ratio was variable, but with no very distinct patterns over time, except possibly during that period here where it was a bit higher, at like females were representing 55% of the fish. The age at maturity decreased sharply during the period when the stock collapsed, and now it's at levels that are below the mean for the old period. Fecundity also showed very large change. It was higher during the beginning of the series, very low during the period of the cold period, and it increased after that in the 2000s. The length at age, here what I present is a kind of standardization for the mean length at age that was calculated for each age, and a mean value for all the ages between 3 and 13 was done after that. So when you have values that are below, it's indicating that for most of the fish, the mean size at age were lower than the mean value. So with those characteristics, we can calculate the total egg production of the stock over the years. So we see that with taking into account those changes, we see that the total egg production decreased very sharply, and that most of this decrease in total egg production is associated with the fact that the stock collapsed. So the number of fish were really low. But if we want to see how those, the different life history threats influence the total egg production, we can calculate a base run where total egg production was estimated from the mean values of all life history threats for all years. So the red line here represents that value. So we see that depending on the time, the total egg production observed is above or below that value. If we divide the two to have an indices of how the total egg production changed over time, we see that it could be between -60 or +100% of the mean value during the old period. So you can have very large change in the total egg production on a relative basis over time. If we compare that to the abundance and fishing mortality and temperature regime that I showed you earlier, the most striking effect is the relation between the temperature and this deviation in the total egg production. We see that in the period where the total egg production was lower than the mean values for the whole period, it's really associated with the cooling of the water masses in the end of the 80s and early 90s. So it seems that temperature regime is explaining a large part of these changes in the total egg production. If we look more closely at what is explaining the deviations in total egg production by comparing the observed total egg production to the total egg production while keeping each parameter at its mean value over the time series. We can estimate, for example, the relative effect of age diversity, sex ratio, growth, maturity, and fecundity on those deviations in total egg production. And what is important to notice is that the importance of each of those life history parameters is not the same all over the years. So their relative importance is not the same. And in some cases, it will have positive or negative effects on the total egg production. And also what we see is that depending on years, it's not the same life history parameters that will influence the deviation in total egg production. And in other cases, these parameters will have cumulative effects on the deviations in eggs production, and in other years, they will have opposite effects. For example, in the first part, we see that it's mostly growth and fecundity that are explaining the positive deviation in total egg production, while after that, it's really it's more the growth that decrease and the older size at maturity that are explaining the negative change in the total egg production. And when the stock collapsed, we see that the age diversity that was really restricted is explaining the large part of the deviation in total egg production. So we see that depending on the situation, these different reproductive characteristics don't have the same weight in explaining those changes. So it's really important to really follow those characteristics over time to understand what is going on in terms of egg production. Now, what is the impact of those changes in the reproductive rate and productivity of the stocks? To do that, what I use is that I calculated reproductive rate based on the lifetime offspring production, which is estimated from the survival probability at age and the number of female offspring that are produced per female at each age. For the non-Gulf of St. Lawrence, I estimated the survival for two groups. The juvenile survival between age 0 and 3 was estimated from the mortality per year, taking into account the number of fish at age 3 in year T, and the total egg production in the year T minus 3. So with those, we could estimate some mortality per year. For adult mortality, I used the natural mortality that is estimated from the sequential population analysis from the Northern Gulf of St. Lawrence. In that stock, before 1986, the value was set at 0.2, like it's done for most cod stocks. Between 86 and 96, the mortality was increased to 0.4 for different reasons, and one of those reasons was that during the moratorium that was put in place between 94 and 97, when people were examining the catch curve from the abundance survey, they estimated that the total mortality was around 0.5 or 0.6, and that there was no fishing during that period. So it was clear that the natural mortality had increased during that period. So for that period, they set the mortality at 0.4. And in the following years, the natural mortality was put in the sequential population analysis as a parameter that was estimated by the analysis. So it gave some values of natural mortality per block of 4 or 5 years during that period. And the egg production of mature female at age was estimated from the different parameters like the maturity and the fecundity at age. With those information, we can estimate the reproductive rate per year. So what we see is that at the beginning of the series, we had positive reproductive rate. And between 86 and 1995, the reproductive rate was below 1, meaning that the females were not producing enough young during their life to replace themselves. So essentially it's saying that the population would not have increased during that period. And there was a large peak in 1 year that was essentially associated with a good survival rate of one cohort. And after that period, the reproductive rate was maintained between, let's say, 2 and 5. And in the recent years, we see that a declining trend again. If we calculate a mean value for those reproductive rates, we can estimate some standard deviation for the juvenile mortality, the adult mortality, and the egg production at each age. We see that there's a large coefficient of variation in the adult mortality. And in the case of the egg production at age, we see that the variability is large at the beginning, essentially due to the changes in the age at maturity in the time series. And it's decreasing after that period, and it's increasing again at the age 10 and more. And that increase in the coefficient of variation for older ages is essentially associated with the variation in the growth rate during the time series. Those mean values indicate that for the old time series, we would have a reproductive rate of 1.45, meaning that without any fishing, the population could have increased by a proportion of 3.8% per year, with a doubling time of 18 years. If we examine the sensitivity of reproductive rate to the variety in juvenile survival, adult survival, and offspring production, we see that the most important factors in explaining the changes in reproductive rate are the adult and juvenile mortality. They're quite more important than the egg production. And the influence of growth, maturation, and fecundity through their impact on offspring production was also estimated, and we see that those don't have an influence that is as large as the mortality, for example. But one of the problems with those type of approach is that we are not taking into account the correlation between, for example, the life history characteristics and also the mortality. Here I did some really simple correlation between the survival and reproductive parameters. And if we examine the length at age 3, which is an indication of the juvenile growth, we see that it's really closely related to the age at maturity. So if fish are larger at age 3, they will mature earlier. And the length also at age 3 is highly correlated to the adult and juvenile mortality. So if you have a larger length at age 3, the mortality will decrease. So if you're growing slower, the mortality will increase. The length at age 6, which represents the mean size of the adult population, is correlated with the fecundity. So if you have a higher growth rate and higher size at age 6, your fecundity will be higher also. So all those things are probably related through the temperature effect on the growth and fecundity, growth condition and fecundity. And there's also a negative relation between mortality of the adults and the length at age 6. So based on those things, we see that larger juvenile size is associated with earlier maturity and lower mortality for juvenile and adults. The larger adult size, which would represent a higher adult growth, is associated with lower adult mortality and higher fecundity. I didn't present the correlation here with the mean annual temperature, but the higher temperatures are associated with higher adult size at age, better condition of the fish, and higher fecundity. And it's also associated with the lower adult mortality. So these correlations suggest that the variation in the reproductive traits are also associated with changes in mortality. And given the large importance of natural mortality on reproductive rate, variation in life history threat determining reproductive potential might have greater importance on the productivity of the stocks than demonstrated by standard sensitivity analysis. There's a large acceptance that growth, maturity, fecundity, and juvenile survival, the recruitment, are variable within population, but due to difficulty of measurement, natural mortality is very often assumed to be species-specific, constant, and independent of size. This has important consequences as it will bias our interpretation of the impact of changes in reproductive potential on stock productivity. Many studies have been done on relationship between life history parameters and mortality, like the size of the fish, the von Bartholin growth parameters, and reproductive effort have been all related in some way to mortality. And those relationships are explained by different hypotheses of trade-offs between life history and M. For example, predation and mortality have been related, predation typically declining with size. Trade-off between reproductive effort and mortality are so assumed, with higher reproductive effort resulting in higher mortality. And there are also some hypotheses based on physiological mechanisms that, because of allometric relationships, will influence metabolic rate, standard dynamic action, aerobic scope that will result in higher mortality in juvenile fish. Here I use an example of possible change in natural mortality with size between years that could be observed. To do that, I use a model that was published last year by Gislason. I don't know if I'm pronouncing the name correctly. And it's essentially estimating the natural mortality based on the length of the fish and the characteristics of the von Bartholin growth curve. The general pattern is interestingly similar to the natural mortality that was obtained from the sequential population analysis for cod in the Northern Gulf of St. Lawrence, if we exclude size effects. So meaning that at the beginning we have higher mortality and there was an improvement over time, and we see again that natural mortality seems to begin to increase again. But I think the most important thing is that it's showing the very large change in M with size. For example, in the model that we are using, we have a mean natural mortality that is equal for all ages. And if we use that type of model, we see that, for example, the mortality at age 3 is much higher than at the age 5, 6, or so on. And the other thing is that there's a decreased variability in the natural mortality between years when it comes to larger fish. So these type of changes can have very important consequences for the reproductive rate and productivity of the stocks. So future studies on reproductive potential should include M as a dynamic parameter instead of just putting it as a constant value. We should then examine what are the links between growth, maturity, and mortality, and the impact on environment and human activities on these relationships. For example, if lower size means higher mortality, temperature will have direct consequences on natural mortality since it will affect growth and maturation. Selective fishing by producing fish of smaller size with higher reproductive investment should increase the natural mortality. So there's a very good example of that by a study of Jorgensen and Vixen. And it could also influence fish behavior. For example, if you have higher predation risk on aggregation of pre-spawning fish, a lower age at maturity could mean that the fish of smaller size will be put into greater predation risk. So this could again increase their mortality. So that type of relationship should be considered into the evaluation. To summarize, the reproductive threats are of variable amplitude. The relative importance over the years is also changing. It's not stable over time. And the covariation between these reproductive characteristics can be cumulative or can have cumulative or opposite effects on total egg production, and reproductive threats have less influence on reproductive rate and productivity than juvenile and adult mortality. However, the relations between life history threats and mortality are not taken into account in all of those studies. Based on the observed variability in life history threats, the trade-offs with ham, and the large importance of ham in stock productivity, the largely accepted assumption of constant species-specific ham in stock assessment should be challenged. The incorporation of reproductive potential information into stock assessment and management needs to take into account the links between life history threats determining the reproductive potential and the natural mortality. And finally, the measure of reproductive potential should be preferred to spawning stock biomass, as they provide information not only on the number of eggs that are produced, but also on the productivity of the stock. Thank you.